SAP Academy once again, and here we are with the new numerical on second law of thermodynamics. So question. A heat pump working on Carnot cycle takes in heat from a reservoir at 5 degrees Celsius and delivers heat to a reservoir at 60 degrees Celsius. So there is a heat pump. So this is heat pump over here, which receives heat from the reservoir at 5 degrees Celsius and rejects it to the 60 degrees Celsius. Right? The heat pump is driven by a reversible heat engine which takes in heat from a reservoir at 40 degrees Celsius and rejects heat to the reservoir at 60 degrees Celsius. So there is a heat engine which takes in heat from the reservoir at 840 degrees Celsius over here and reject heat to the again sink at 60 degrees Celsius. The reservoir heat engine also drives a machine that absorbs 30 kilowatt. So whatever the heat engine delivers the work output, so out of that, some part of that work output is given to the machine, which takes 30 kilowatt, and the remaining work output from the heat engine is supplied to the heat pump. To determine the rate of heat supply from 840 degrees Celsius source, so how much amount of Q1 is supplied to the heat engine from the source, right, at 840 degrees Celsius. Next is the rate of heat rejection to the 60 degrees Celsius sink. So there is a sink over here. So how much amount of total heat is rejected to this sink by heat pump and by heat engine. So heat engine delivers Q2 amount of heat to the sink and heat pump delivers Q4 amount of heat to the sink. So total Q4 plus Q2, that is what total heat rejected to the sink. So that we have to find out. Okay. So first of all, the given parameters are T1, that is 840 degrees Celsius, that is the source temperature for the heat engine, and in Kelvin it is 1113 Kelvin. T2, it is the sink temperature, right? It is also called as the T4 because the heat pump also rejects that heat. That's why it is T2 equal to T4, and the temperature is 60 degrees Celsius. So in Kelvin, 333 Kelvin. Then we have the source for the heat pump, that is what 5 degrees Celsius and in Kelvin 278 Kelvin. And the amount of heat absorbed by the heat pump from the source is how much? 17 kilowatt. And here we know that there is a machine which absorbs the heat of 30 kilowatt from the part of heat generated by the or work output given by the heat engine. Okay, that's why. So we can write the total work of heat engine equal to work given to the heat pump plus 30 for the machine. Okay, that is what the given condition. Now let's solve the problem step by step. So very first thing that we have to find out is what? Q1. The very first unknown is what? Q1 for this problem, right? So Q1 is unknown. Next we have to find out this rate of heat rejection to the sink. So Q2 and Q4 is unknown over here, right? And we have to find out total amount of heat rejected to the sink. So that's why Q2 plus Q4, right? So step by step we will find out now Q2 and Q4. So very first we will go with the Q4, right? Now how can I find out the Q4 over here? If I apply, Q4 is related to the heat pump. So if I apply the first law of thermodynamics to this heat pump, that is what? Summation of heat equal to summation of work, right? So if I apply this first law of thermodynamics, I'll get this equation that Q4 equal to Q3 plus work given to the work input to the heat pump, right? So now in this equation, what is unknown over here? So unknown here is work given to the heat pump because Q3 is known to us, that is 17 kilowatt. So in order to find out Q4 over here, we need to find out what exactly is the work input given to the heat pump. So how do I find out that? Do we have another equation for that? Yes. As we have this given that the heat pump is Carnot heat pump, then we can find out that heat pump we input using the COP, right? So we have COP equation, that is Q for heat rejected by the heat pump divided by input required to reject that heat, right? The COP of heat pump equal to Q4 upon WHP, that is input given to the pump. Now again in this case, in order to find out Q4, the COP is unknown, right? So we need the COP of the heat pump. As this heat pump is a Carnot heat pump, we can use the temperature relation to find out the COP, right? So that is what the COP of heat pump, Carnot heat pump is equal to heat rejected temperature divided by temperature difference of heat rejected and source temperature, right? The COP of heat pump we can find out like this. Okay. So now we have COP, that is what the equation that we have seen right now, right? So if I put the values for these parameters, for these temperatures, we can find out easily the COP. So T4 here is 333 Kelvin and T3 is given here or is 278, that is 5 degrees Celsius. Okay. So if I put these values, I'll get the COP as 6.051. Now we got the COP, right? Now we can put the value of this COP in earlier equation, that is COP equal to Q4 upon WHP. So that was the relation that we have seen earlier. Now we also know that Q4 is also equal to, you can see here, so Q4 is also equal to Q3 plus WHP. So Q3 plus WHP. And we know the value of Q3, that is 7. Now if you look at that is equal to COP. So COP value that we have got 6.051. Now look at this last equation over here. So in this relation, only unknown is WHP, that is input given to the heat pump. So if I have only one equation and there is only one unknown, then I can easily find out WHP, right? So WHP comes out to be equal to 3.365 kilowatt. Now we got the WHP. Now if I put the value of this WHP in the relation, what is that? If you see here, whatever the heat or output given by the heat engine is, that is given to, part of it given to the heat pump and some amount of that is given to the machine. So amount of work output given to the machine is 30 kilowatt, that is given. So we can write that WHE is equal to WHP plus 30 kilowatt, right? So this way we can write it. WHE equal to WHP plus 30. Now just now we got this WHP 3.365. So if you put the values, you will get that amount of heat generated by the heat engine. Okay, amount of heat generated by amount of work output given by the heat engine. So that is what 33.365 kilowatt. Okay. Now we got this one. We need to find out Q4 now. That was our target, right? So we need to find out Q4 over here. So how do we find out that? The Q4 is equal to Q3 plus WH, right? Q3 is 17 and WHV just now we calculated that 3.365. So put करने के बाद क्या मिल जाएगा? The Q4 value, that is heat rejected by the heat pump to the sink, 20.365 kilowatt. So out of two values, that is Q2 and Q4, we got Q4. Now let's go for the Q2, right? Now only unknown is what? Q2 over here, right? So how do we find the Q2 over here? The Q2 is in relation to the heat engine. So how do we find that? Do we have any relation? Yes, there is. What is that? So if I apply first law of thermodynamics to this heat engine again, right, we get equation like this. So Q1 heat supplied to the heat engine is equal to work output given by the engine and Q2 rejected to the sink by the heat engine, right? So Q1 input given to the engine equal to work output given by that engine plus it rejected to the sink, right? Now in this case we need to find out this Q2. But to find out this Q2, we need to find out the Q1 also, right? Because WHE, that is work output that given by the heat engine that we have just got, that value, right? So only need is Q1 there. So how do we find that Q1 there? Yes, there is another relation of efficiency. So we can use the relation of efficiency of heating engine, that is what this. We know that efficiency of heat engine is equal to work output given by the engine divided by input heat given to the heating engine, right? Now in this case, we need to find out we need to find out Q1, right? Because we know this value, work output given by the engine is known to us. But in order to find out this Q1, we need to find out efficiency of heat engine also. So as this heat engine is a reversible heat engine, we can use the relation of temperature, right? So efficiency formula in form of temperature. So that is what here. Okay. So efficiency of heat engine equal to T1 minus T2 upon T1, right? So source temperature minus sink temperature divided by source temperature. Okay. Put करने के बाद क्या मिल जाएगा? Efficiency of heat engine. So that is what the efficiency of heat engine. Now we got the efficiency of heat engine. If you put the value over here, so value of efficiency is here and WHE is just we got that value. Put करने के बाद only unknown बच जाएगा Q1. The Q1 value is 47.66 kilowatt. Now we got the Q1. We can put this in this relation to find out this Q2. So this way we can put these values to find out this, right? So easily we can find out now Q2. So Q2 comes out to be equal to 14.295 kilowatt. Now we got Q4 and we got Q2 also. That means we can easily find out now how much amount of heat is rejected to the sink, right? What is that? Total heat rejection to sink at temperature 60 degrees Celsius. That is equal to Q4 plus Q. So put करने के बाद तो Q2 value is 14.295 and Q4 value is 20.365. Put करने के बाद दोनों का एडिशन मिल जाएगा 34.66 किलो. This is what total heat rejected to the sink, right? And another unknown was this Q1. So that we have got this value Q1 over here. Okay. So this way easily we can find out the solution to our numerical. Thank you.